Okay, so now we're ready to start section 5.3, which is about the fundamental theorem of calculus. And this theorem comes in two different parts. So we'll start with the first one. And we need to set up a few things in the background. So let's say we have a function f. So let f be continuous on the closed interval a to b. That's what you need in the background before you can state this theorem. And it actually really helps to have a picture available. And I'm actually going to use the letter T for the horizontal axis here because I want to reserve x for something else. So this is going to be maybe the graph of what the function f looks like. And let's label a and b here. So I just want to divide those up there. So because we really only need to assume that the function f is continuous between a and b. And I've drawn it so that it extends beyond b to the right and beyond a to the left, but that is not really what we're going to be looking at. But at least this is certainly a picture of a function that is continuous on the closed interval a to b, but this is all we're actually assuming. Okay, what we're going to do now is we're going to use this picture now to define a new function g. So define the function g on the closed interval a to b using the following rule. And this is what I said, why I said I was going to reserve x for something else, because I want to use x for the input value for the function g. I want to use it for the parameter. And here's the way this function works. If you want to plug a value x into g, here's what you do. Well, and it's only going to work for values of x that lie between a and b. So what I do is I go like this, and I label my x on the t-axis in this picture, and then I use that value to slice this up like that, and then I measure, and I'm going to write it in blue here first, I measure this area. So g of x represents the area of this shape here. That's what g of x is actually measuring. So I can write that down symbolically using this. I can write down g of x is actually the definite integral from a to x. And now I'm going to just say the function f of t with respect to t. So it's the area under this graph where a and x are my left and right endpoints. Okay, so that's what you're actually measuring. Now, up till now, I haven't stated the theorem yet. I haven't told you what the fundamental theorem of calculus is, but now we're ready to state it. So the theorem, and I'm going to abbreviate it FTOC with the Roman numeral 1. This is just part 1 of the fundamental theorem of calculus. And because we've set up all this stuff in the background, the theorem just says the following. It just says that this function g is smooth, or in other words, differentiable. And if you take the derivative of g at the point x, you just get f of x. And that's true for every x in the closed interval a to b. So that is the fundamental theorem of calculus part 1. And I do like to encourage people to think of the theorem in a visual way. And here's what I mean by that. So I'm going to put IE. In other words, that is. So I'm just going to reformulate what I just said in slightly different words, or in this case, notation. But I like to suggest that you think about it this way. If I take the derivative with respect to x of this definite integral, which is a function of x, because actually I'll write this down, then I'm going to make another comment about why you should be convinced that this truly is a function of x. Think about it this way. If I move x to the right, this green area gets larger. And if I move x to the left, that green area gets smaller. So the area here really truly is a function of x, and the area can be expressed using this definite integral. So that's why this truly is a function of x. So if you were to take its derivative with respect to x, the fundamental theorem of calculus tells you that you can just do this. You can say, okay, the derivative cancels with the definite integral, and the x up top, which is my upper bound, just falls right in place for the t. And then what you get is f of x. And one common question that comes up is, well, what happens to the a? And the answer is nothing. It's not used. It plays no role in the derivative of this function. And the reason for that is, remember what, because this really, the left-hand side here, this is really g prime of x. Right? G prime of x stands for the rate of change of g of x with respect to x. In other words, if I move x a little bit, how fast is the area g of x changing? Well, if I move this x towards b to the right, the area is going to change. Well, how fast is it going to change? Well, it's going to depend on two things: how fast I move x, and also the graph of this function f. But it's certainly not going to depend on a. Right? The actual area will depend on a, but the rate at which that area is changing will only depend on the function itself and the rate at which I move x. So in other words, that's why it doesn't depend on a. So that's an informal explanation. I certainly don't want you to interpret that as some sort of a rigorous proof. I did not prove to you that this theorem is true, but this is just a rough explanation about why some of the things work the way they do. But we're not going to prove this in detail. But we are going to cover a few examples on how to use it. Maybe this is a good place to stop the clip, though.